Welcome to Deep Science Sleep. Close your eyes for a moment and imagine yourself floating in perfect stillness. You're suspended in the softest darkness imaginable, weightless and completely at peace. There's nothing to hold you down, nothing to worry about, just the gentle embrace of the cosmos surrounding you in every direction. The temperature is perfectly comfortable, neither warm nor cool, and you feel yourself beginning to drift, beginning to let go of the day's concerns as we embark together on a journey through the most peaceful mysteries our universe has to offer. Tonight, we're going to explore the unknown, but not in a way that makes you anxious or keeps you awake. Instead, we'll wander through cosmic enigmas that are so vast, so far beyond our everyday concerns, that contemplating them brings a strange kind of comfort. These are mysteries that have puzzled scientists for decades, questions without answers that stretch across billions of light years, phenomena so immense and timeless that your own worries begin to feel beautifully, peacefully small in comparison. So settle deeper into your pillow, adjust your blankets to that perfect position, and let your breathing slow naturally. There's nowhere you need to be, nothing you need to do. Just listen, drift, and let these cosmic wonders carry you gently towards sleep. The universe has been unfolding its mysteries for almost 14 billion years, and it will continue long after we're gone. Tonight, we're simply going to float among them for a while, letting their vastness and their beauty wash over us like waves on a distant shore. The invisible universe, dark matter's hidden presence. As you lie there in the darkness of your room, consider this: the darkness around you is not really empty. In fact, most of the universe is made of something we cannot see, cannot touch, and cannot directly detect with any instrument we've ever built. This invisible substance is called dark matter, and it makes up roughly 25% of everything that exists. The atoms that form your body, the bed beneath you, the air you're breathing, the earth itself, and every star you've ever seen in the night sky together account for less than 5% of the universe. The rest is hidden from us, working its influence in ways we can observe but cannot fully understand. Scientists first suspected dark matter's existence back in the 1930s when an astronomer named Fritz Zwicky was studying the Coma Cluster, a vast collection of galaxies bound together by gravity. He noticed something peculiar. The galaxies were moving much faster than they should have been. According to the laws of physics, they were traveling so fast that they should have escaped the cluster's gravitational pull entirely, flying off into the void of space like sparks from a campfire rising into the night. Yet there they remained, held in place by something invisible, something with enormous gravitational mass that no one could see. Imagine for a moment that you're watching a mobile hanging from the ceiling, the kind with delicate shapes suspended on thin wires that turn slowly in the air. Now imagine that the shapes are spinning and moving in ways that seem impossible based on what you can see. They're circling faster than they should, pulled by invisible forces. That's essentially what Zwicky observed when he looked at those galaxies. Something unseen was there, something with immense gravitational power, anchoring those galaxies in place like invisible weights on an invisible scale. Decades passed before other scientists took Zwicky's ideas seriously. In the 1970s, astronomer Vera Rubin made observations that would revolutionize our understanding of the cosmos. She was studying spiral galaxies, those beautiful pinwheel shapes scattered throughout the universe, measuring how fast different parts of them were rotating. According to the laws of physics as we understood them, stars on the outer edges of these galaxies should be moving more slowly than stars near the center, just as planets farther from the sun move more slowly in their orbits than planets closer in. But that's not what Rubin found. Instead, she discovered that stars at the outer reaches of galaxies were moving just as fast as those near the center, sometimes even faster. Picture a spinning carousel at night with lights along its edge. If you were far away, you might notice that the lights on the outer rim are moving much faster through space than lights near the center, even though they're all rotating at the same speed. That's because they have farther to travel in each rotation. Now imagine that the outer lights were actually moving at the same speed through space as the inner lights. That would mean something was wrong with your understanding of how the carousel works. That's exactly what Vera Rubin discovered. The rotation curves of galaxies, as they're called, defied our understanding of gravity and motion. The only explanation that made sense was that galaxies are embedded in enormous halos of invisible matter, dark matter that extends far beyond the visible edges of the galaxy, providing additional gravitational pull that keeps those outer stars moving faster than they otherwise would. These dark matter halos are immense, stretching out hundreds of thousands of light years beyond where the visible stars end. If you could somehow see dark matter, galaxies would look completely different, appearing as vast spherical clouds of this mysterious substance with the bright points of stars and gas merely decorating their innermost regions. Scientists have spent decades trying to figure out what dark matter actually is. The leading theory suggests it's made of particles that don't interact with light at all, particles that can pass right through ordinary matter as though it weren't even there. Every second, trillions upon trillions of these dark matter particles might be streaming through your body, passing through the earth, through buildings and mountains and oceans, completely unaffected and undetectable. It's a strange thought, isn't it? That you might be constantly bathed in a river of invisible particles that you can never feel or see, that flow through you like water through a ghost. Physicists have proposed various candidates for what dark matter particles might be. One possibility is something called a WIMP, which stands for Weakly Interacting Massive Particle. These hypothetical particles would have mass but would interact only through gravity and possibly through the weak nuclear force, one of the fundamental forces of nature. Despite their name, WIMPs would be quite substantial in terms of mass, perhaps tens or hundreds of times heavier than a proton. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays and other interference, hoping to catch just one of these particles interacting with ordinary matter. So far, despite years of searching with increasingly sophisticated equipment, no one has detected a single WIMP with certainty. Another candidate is the axion, a much lighter particle that was originally proposed to solve a different problem in physics but might also explain dark matter. Axions would be incredibly light, perhaps a trillion times lighter than an electron, yet they would be so numerous that their combined mass could account for all the dark matter in the universe. They're named after a brand of laundry detergent because they were supposed to clean up a problem in particle physics, which gives you some sense of physicists' sense of humor. Detecting axions would require completely different approaches than detecting WIMPs, and experiments are currently underway to search for them as well. Some scientists have proposed even more exotic possibilities. Perhaps dark matter consists of primordial black holes, tiny black holes that formed in the first fractions of a second after the Big Bang, each one smaller than an atom but containing as much mass as a mountain or a moon. Or maybe dark matter is made of particles that exist in a different dimension that we cannot access, interacting with our universe only through gravity. Or perhaps our understanding of gravity itself is incomplete, and what we interpret as dark matter is actually evidence that gravity works differently on the largest scales than we thought. This last idea is called modified Newtonian dynamics, or MOND, and while it has some successes in explaining galaxy rotation curves, it struggles to account for other observations. The beautiful thing about dark matter, from the perspective of someone trying to fall asleep, is that it's everywhere and nowhere at once. It permeates the space between galaxies like an invisible fog, creating a cosmic web of gravitational influence that shaped how matter clumped together in the early universe. When scientists create computer simulations of how the universe evolved, starting from the nearly uniform soup of matter that existed shortly after the Big Bang and fast-forwarding through billions of years of cosmic history, they find that dark matter forms a scaffolding, a framework along which ordinary matter can condense to form galaxies and galaxy clusters. Without dark matter, the universe would look completely different. Galaxies might never have formed at all, or they would have formed much more slowly, and you wouldn't be here contemplating these mysteries because the cosmic conditions necessary for stars and planets and life would never have arisen. The gravitational lensing effect provides some of the most striking evidence for dark matter's existence. When light from distant galaxies passes through or near a massive object like a galaxy cluster, the intense gravitational field bends the path of that light, just as a lens bends light rays. This was one of the predictions of Einstein's general theory of relativity, and it's been confirmed countless times. But here's the interesting part. When astronomers map out how much light bending is occurring around certain galaxy clusters, they find far more gravitational lensing than can be accounted for by the visible matter alone. It's as though there's an invisible lens made of something we cannot see, distorting and magnifying the light from background galaxies. That invisible lens is dark matter. One of the most famous examples is the Bullet Cluster, a pair of galaxy clusters that collided with each other millions of years ago. When scientists studied the aftermath of this collision, they found something remarkable. The hot gas from the two clusters, which we can detect because it emits X-rays, had slowed down and clumped together in the middle where the collision occurred, as you'd expect from normal matter running into other matter. But the gravitational lensing map showed that most of the mass, and therefore the gravitational pull, was in two separate regions that had passed right through the collision zone without slowing down. The dark matter from each cluster had simply passed through, like two clouds of fog moving through each other, completely unimpeded. This is strong evidence that dark matter really is something fundamentally different from ordinary matter, something that doesn't collide or interact in the ways we're used to. And yet, despite all this evidence, despite the mathematical models and the computer simulations and the observations from hundreds of telescopes around the world and in space, we still don't know what dark matter is. It remains one of the greatest unsolved mysteries in all of physics. Somewhere out there in the darkness, making up the majority of the universe's mass, is something that science has not yet identified. It's humbling, really. We've sent probes to the edge of the solar system. We've detected gravitational waves from colliding black holes billions of light years away. We've photographed the cosmic microwave background radiation from the earliest moments of the universe, and yet we cannot identify the substance that makes up most of the matter in existence. Let that thought settle over you as you sink deeper into your pillow. The universe is mostly unknown. Most of what exists is hidden from us, working its influence in ways we can measure but not yet understand. There's something peaceful about acknowledging the limits of human knowledge, about recognizing that despite all our achievements and discoveries, the cosmos still holds secrets that dwarf our understanding. Dark matter surrounds us, supports the structure of galaxies, made possible the formation of the solar system and the planet beneath you, and yet it remains as mysterious today as it was when Fritz Zwicky first suspected its existence nearly a century ago. Some mysteries don't demand solutions. Sometimes it's enough to know that they're there, like the quiet presence of an old friend, steady and dependable even if we don't fully understand them. As you breathe slowly in and out, imagine dark matter as a gentle, invisible ocean in which everything floats. Galaxies are islands in this ocean, and you, lying in your bed, are part of one of those islands, surrounded on all sides by something vast and unknowable. It's there in the space between the atoms of your body, in the air above you, in the ground below you, passing through everything without leaving a trace. It's been there for billions of years and will be there for billions more. In a universe made mostly of mystery, perhaps the most honest response is simply to rest, to acknowledge the unknown, and to let it be. Dark energy, the force tearing everything apart. If dark matter is the mysterious substance that holds galaxies together, then dark energy is its equally mysterious counterpart, the force that's pushing the entire universe apart. And unlike dark matter, which makes up about 25% of the universe, dark energy accounts for roughly 70% of everything that exists. Together, dark matter and dark energy make up 95% of the cosmos, which means that all the atoms, all the stars, all the planets, all the galaxies, everything you can see or touch or detect with any conventional instrument, amounts to a mere 5% of reality. It's as though we're living in a house where we can only see and interact with one room out of 20, while the other 19 rooms remain forever locked and hidden from our view. The story of dark energy's discovery is one of the most fascinating in modern science. A tale of how an unwanted result turned into a revolution in our understanding of the cosmos. In the 1990s, two teams of astronomers were engaged in a friendly competition to measure the rate at which the universe's expansion was slowing down. You see, everyone knew the universe was expanding. Edwin Hubble had discovered that back in the 1920s when he observed that distant galaxies were moving away from us, and the farther away they were, the faster they appeared to be receding. This expansion was understood to be a leftover from the Big Bang, the explosive beginning of space and time itself. But gravity, pulling everything back together, should be gradually slowing down that expansion, like a ball thrown into the air that gradually slows as Earth's gravity pulls it back down. Both teams were using a particular type of exploding star called a Type Ia supernova as a standard candle, a way of measuring cosmic distances. These supernovae occur when a white dwarf star accumulates too much matter from a companion star and crosses a critical threshold, causing a catastrophic explosion that briefly outshines an entire galaxy. Because these explosions happen at roughly the same threshold every time, they always reach approximately the same peak brightness, which means astronomers can use them as distance markers. By comparing how bright a Type Ia supernova appears from Earth to how bright it should be intrinsically, scientists can calculate how far away it is. It's like seeing a 60-watt light bulb in the distance and knowing how bright a 60-watt bulb should be, figuring out how far away it must be based on how dim it appears. Both teams expected to measure a deceleration in the universe's expansion, a gradual slowing down. They expected to find evidence that gravity was winning its battle against the expansion, even if it wasn't winning fast enough to eventually pull everything back together into a big crunch. But that's not what they found. In 1998, both teams independently announced results that shocked the scientific community. The expansion of the universe wasn't slowing down at all. It was speeding up. Imagine you're watching a film of someone throwing a ball into the air, and as the ball rises, instead of slowing down as it should, it starts accelerating upward, moving faster and faster as it climbs higher. That would violate everything you know about how gravity works. That's essentially what these astronomers discovered was happening to the universe. Something was pushing against gravity, some mysterious repulsive force that was accelerating the expansion of space itself. The scientists called this mysterious force dark energy, not because it was dark in color or composition, but because it was completely unknown, as obscure and hidden as dark matter. The implications of this discovery are profound and, in a strange way, rather peaceful to contemplate as you're falling asleep. It means that the universe is not just expanding but accelerating in its expansion. Galaxies are moving away from each other faster and faster, and this acceleration is increasing over time. In the unimaginably distant future, billions and billions of years from now, this acceleration will have carried most galaxies so far apart that they'll be beyond each other's observable horizons. An observer in a distant galaxy will look out into space and see nothing but their own galaxy, surrounded by darkness. The cosmic web of galaxies and clusters and superclusters that we can observe today will have dissolved into isolated islands of matter, each one alone in an expanding void. But what is dark energy? That's the question that's plagued physicists and cosmologists for more than 2 decades now. The honest answer is that no one really knows. There are theories and ideas and mathematical models, but no definitive answer. One possibility is that dark energy is simply a property of space itself, what Einstein called the cosmological constant. In this view, empty space has an intrinsic energy associated with it, a sort of background energy woven into the fabric of the universe. As space expands and new space comes into existence, more dark energy is created, and this energy has a repulsive gravitational effect that pushes things apart. It sounds paradoxical, doesn't it? That gravity could push instead of pull? But in Einstein's general relativity, the equations allow for exactly this kind of behavior under certain conditions. Think about it this way. Imagine space itself as a kind of elastic fabric that's constantly being stretched. But unlike a normal elastic material that wants to contract back to its original size, this fabric becomes more energetic the more it's stretched, and that energy drives further stretching. It's like a spring that gets stronger the more you extend it instead of weaker, or a rubber band that pulls harder as it lengthens. That's essentially what dark energy does to space. The more space expands, the more dark energy there is, and the more dark energy there is, the faster space expands. It's a feedback loop that has been accelerating for billions of years. Another possibility is that dark energy isn't constant at all, but is instead a dynamical field that changes over time, something physicists call quintessence. In this model, dark energy would be somewhat like a field that permeates all of space, similar to how a magnetic field permeates the region around a magnet. This field would have its own properties and could evolve as the universe ages, potentially growing stronger or weaker with time. The name quintessence comes from ancient Greek philosophy, where it referred to the fifth element beyond earth, air, fire, and water, a celestial substance that filled the heavens. It's a poetic name for something that remains, in essence, completely mysterious. Some scientists have proposed even more radical ideas. Perhaps our understanding of gravity itself is incomplete, and what we interpret as dark energy is actually evidence that Einstein's general relativity needs modification on the largest cosmic scales. Or maybe we're living in a universe with extra dimensions beyond the three spatial dimensions and one time dimension we're familiar with, and dark energy is somehow related to those hidden dimensions. Or perhaps, in an idea that sounds more like science fiction than science, we're living in a false vacuum, a state that appears stable but could theoretically decay into a lower energy state at any moment, fundamentally changing the laws of physics throughout the universe in an expanding bubble moving at the speed of light. The search for answers continues. Astronomers are conducting ever more precise observations of distant supernovae, mapping the distribution of galaxies across cosmic time, studying the cosmic microwave background radiation for subtle clues about dark energy's properties. They're looking at how galaxy clusters have evolved over billions of years, how the cosmic web has grown and changed, searching for any hint that might reveal dark energy's true nature. Particle physicists are exploring quantum field theory, trying to understand if and how the quantum vacuum might contribute to dark energy. Theorists are developing new models and new mathematical frameworks, pushing the boundaries of our understanding of space and time and gravity. And yet, despite all this effort, dark energy remains as mysterious as it was in 1998. We know it's there because we can measure its effects. We know it makes up the majority of the universe's energy budget. We know it's causing the universe to expand at an accelerating rate. But we don't know what it is, and we don't know why it has the particular strength it does. This is sometimes called the cosmological constant problem. Calculations based on quantum field theory suggest that the vacuum energy of space should be vastly larger than what we observe, larger by a factor of 10 to the power of 120, which is a 1 followed by 120 zeros. That's one of the largest discrepancies between theory and observation in all of physics. There's something oddly comforting about dark energy as you're drifting off to sleep. It's the ultimate example of letting go, of expansion without resistance, of things moving farther and farther apart until they vanish beyond distant horizons. The universe itself is teaching us about release, about how holding on isn't always possible or necessary. Galaxies are receding from each other, carried along by the expansion of space, and there's nothing that can stop it or reverse it. In billions of years, this process will leave each galaxy cluster as an island universe, alone in an ocean of darkness, but that's billions of years away, an incomprehensible span of time that has nothing to do with your life or your concerns or the immediate comfort of your bed. Right now, at this moment, you can rest in the knowledge that the universe is vast beyond imagining and operating according to laws we're only beginning to understand. Dark energy is out there, in the space between galaxies, in the fabric of the cosmos itself, gently pushing everything apart with a force so subtle that it only becomes noticeable over distances of millions and billions of light years. On human scales, on the scale of your room or your city or even your planet, dark energy has no effect at all. Gravity is far stronger here, holding you to the Earth, holding the Earth in orbit around the Sun, holding the solar system together. but look far enough out, to the spaces between galaxy clusters and beyond, and dark energy dominates, patient and inexorable, the universe's quiet exhalation that will continue for all of time. Breathe with the universe for a moment. Inhale slowly, feeling your chest expand. Exhale slowly, feeling your body relax and settle. The universe is doing something similar on an unimaginably larger scale, expanding outward in all directions, releasing and letting go. There's a rhythm to it, a slow cosmic breath that's been continuing for billions of years and will continue for billions more. You're part of that universe, made of atoms forged in the hearts of stars, lying on a planet that's orbiting a star in a galaxy that's slowly drifting through the cosmos, carried along by forces you cannot see or feel. Everything is connected, everything is in motion, and at the same time, everything is perfectly fine right where it is. Close your eyes and feel yourself expanding with the universe, letting go of tension, releasing the day's concerns, spreading out into peaceful, comfortable darkness. Strange signals from the depths, radio mysteries. Somewhere out in the depths of space, approximately 15,000 light-years from Earth, there's something sending signals in our direction. Every 44 minutes, like clockwork, this mysterious object releases a burst of radio waves and X-rays that lasts for about 2 minutes. Astronomers have designated it ESCAP J 1832-0911, and they have no idea what it is. It might be a magnetar, the collapsed core of a dead star with magnetic fields trillions of times stronger than Earth's. It might be a binary system where two dead stars orbit each other in a cosmic dance. Or it might be something entirely new, a type of astronomical object that science has not yet classified or understood. The signals continue, regular as a cosmic heartbeat, carrying information across the vast emptiness of space, and we're only beginning to learn how to listen. Radio astronomy has revealed a universe far stranger than anything we can see with optical telescopes. When we look at the sky with our eyes or with traditional telescopes that observe visible light, we see stars and galaxies and nebulae beautiful and familiar. But when we listen to the sky with radio telescopes, giant dish-shaped antennas or arrays of antennas spread across miles of desert or grassland, we detect an entirely different cosmos, one that crackles and pulses and erupts with phenomena that have no visible counterpart. It's like discovering that the world around you is filled with music you couldn't hear before because it was always playing in frequencies beyond your range of perception. Now that we can hear it, we're discovering that the universe is far more dynamic, far stranger, far more alive with activity than we ever imagined. Fast radio bursts, or FRBs, are among the most puzzling of these phenomena. They're incredibly brief flashes of radio waves, typically lasting only a few thousandths of a second, but in that tiny fraction of time, they release as much energy as the sun emits in an entire year. Imagine a cosmic camera flash, but instead of light, it's radio waves, and instead of lighting up a room for a moment, it briefly outshines hundreds of billions of stars. These bursts were first detected in 2007 when an astronomer was digging through archival data from the Parkes radio telescope in Australia, and since then, astronomers have detected hundreds of them, originating from galaxies billions of light-years away. Most FRBs happen once and never repeat, which makes them incredibly difficult to study. By the time you realize you've detected one, it's already over, and you have no way of predicting where or when the next one will occur. It's like trying to study lightning by randomly looking at the sky and hoping to see a flash. However, a small percentage of FRBs are repeaters, sources that emit multiple bursts over time. These repeating FRBs have become objects of intense scrutiny because they can be studied in more detail, monitored continuously, and analyzed for patterns that might reveal their origin. The leading theory is that FRBs come from magnetars, those extraordinarily dense stellar remnants with magnetic fields of unimaginable strength. A magnetar is what's left when a massive star explodes in a supernova, leaving behind a core so dense that a teaspoon of its material would weigh about 1 billion tons on Earth. The surface of a magnetar is a nightmare landscape where the laws of physics as we normally experience them break down completely. The magnetic field is so intense that atoms are stretched into thin needle shapes, and empty space itself becomes birefringent, meaning it bends light differently depending on its polarization, like a crystal. In such extreme conditions, it's thought that sudden shifts or cracks in the magnetar's crust could release tremendous bursts of energy, including the radio waves we detect as FRBs. In 2022, astronomers got a lucky break. They were monitoring a magnetar in our own galaxy, designated SGR 1935+2154, using 2 NASA X-ray telescopes, and they happened to be watching at exactly the right moment when the magnetar produced a fast radio burst. This was the first time anyone had observed an FRB in real time with multiple instruments, and what they saw was fascinating. The magnetar suddenly underwent what's called a glitch, a rapid spin down where its rotation rate abruptly decreased, and shortly after this glitch, the fast radio burst occurred. It was like watching the mechanism of a clock suddenly jam and then release with a burst of energy. This observation provided strong evidence that magnetars are indeed responsible for at least some FRBs. But many questions remain. Then there are the long-period transients, mysterious sources that emit periodic bursts of radio waves, but with much longer intervals between bursts. ESCAP J 1832-0911, which we mentioned earlier, is one example, pulsing every 44 minutes. Another object, discovered in 2024, emits powerful bursts every hour. These timescales are far too long to be explained by normal pulsars, which are rotating neutron stars that sweep beams of radio waves across space like cosmic lighthouses, typically pulsing many times per second or at most every few seconds. Something different must be going on with these long-period transients. But what? One possibility is that they're magnetars or white dwarfs with extremely strong magnetic fields, orbiting in binary systems. Perhaps the interaction between the magnetic fields of 2 stellar remnants, as they spiral around each other, somehow generates these long-period bursts. Another possibility is that these are solitary magnetars or white dwarfs that are rotating extremely slowly, much more slowly than any known pulsar. But the energy requirements are puzzling. How can something rotating so slowly generate such powerful bursts of radiation? It's as though you had a bicycle dynamo that normally needs to be spun rapidly to produce electricity, but somehow this one produces bright flashes of light even when it's barely moving. The physics doesn't quite add up, which suggests we're missing something important about how these objects work. And then there's the famous WOW signal, perhaps the most tantalizing radio mystery of all. On August 15, 1977, the Big Ear radio telescope in Ohio was scanning the sky as part of the search for extraterrestrial intelligence, or SETI, when it detected a signal unlike anything it had recorded before. The signal came from the direction of the constellation Sagittarius and lasted for exactly 72 seconds, which was the precise amount of time it took for the rotation of the Earth to carry that patch of sky through the telescope's field of view. The signal was strong, narrowband, and at a frequency close to 1420 MHz, the emission line of hydrogen, which many scientists believe would be a logical frequency for any technological civilization to use for interstellar communication because hydrogen is the most common element in the universe. A volunteer astronomer named Jerry Emin was reviewing the telescope's computer printout a few days later when he noticed the signal. The computer recorded intensity values as numbers and letters, with higher values indicating stronger signals. Most of the printout was filled with low values, 1s and 2s, occasionally 3s, representing random noise. But one sequence stood out starkly, 6EQUJ5. This represented a signal that rose smoothly from baseline to a peak and then decreased again. Exactly the pattern you'd expect from a continuous signal source passing through the telescope's beam as Earth rotated. Emin was so startled that he circled the sequence on the printout and wrote, "Wow!" in the margin, and that exclamation has been the signal's name ever since. The "wow" signal has never been detected again. The Big Ear telescope continued operating for years, frequently revisiting that same region of sky, but the signal never repeated. Other radio telescopes around the world have also searched for it with increasingly sensitive equipment and found nothing. This is frustrating for scientists because a signal that occurs only once is nearly impossible to study or verify. Was it truly from an extraterrestrial source, or was it just an unusual natural phenomenon? Perhaps a burst from a comet or a piece of space debris that happened to be in the right position at the right time. Or might it have been interference from Earth, some satellite or aircraft or other human-made signal that somehow found its way into the data despite all the precautions? Several explanations have been proposed over the years. In 2017, an astronomer suggested that the signal might have been caused by a hydrogen cloud surrounding two comets that happened to be passing through that region of the sky at the time. Comets do emit radio waves at the hydrogen frequency as the sun's radiation breaks apart the water molecules in their comas, releasing hydrogen atoms. However, other scientists pointed out problems with this explanation, including the fact that comets typically don't produce signals strong enough or narrowband enough to match what was observed. The mystery remains unsolved. There's something hauntingly poetic about these unexplained signals from space. They're like messages in bottles floating across an ocean, except the ocean is the vast emptiness between stars, and the messages might not be messages at all, just the natural conversation of the universe with itself, phenomena we don't yet understand making sounds we've only recently learned to hear. Each burst, each pulse, each mysterious transmission is a reminder that the cosmos is far from silent. It's alive with activity, with energetic events occurring constantly across unimaginable distances, and we're only beginning to develop the tools and the knowledge to interpret what we're detecting. As you lie in bed, feeling yourself relaxing deeper with each breath, imagine those radio waves passing through your room right now, undetectable to your senses but real nonetheless. Radio waves from distant pulsars, from galaxies with active supermassive black holes at their centers, from magnetars and quasars and who knows what else, all of them traveling across space at the speed of light, some of them journeying for billions of years before passing through the air above you and continuing on into the cosmos beyond. You're bathed in an ocean of invisible radiation, most of it completely harmless, carrying information about distant corners of the universe that no one may ever decode or understand. The universe is speaking in languages we're only beginning to learn. Each mysterious signal is a word in a cosmic vocabulary that might take centuries or millennia to fully comprehend. And that's okay. There's no rush. The signals will keep coming, the telescopes will keep listening, and slowly, piece by piece, scientists will figure out more of what it all means. But for now, for tonight, it's enough to know that out there in the darkness 15,000 light-years away, something is broadcasting every 44 minutes, and somewhere else, billions of light-years distant, fast radio bursts are erupting with the energy of entire suns, and 47 years ago, a signal called WOW appeared for 72 seconds and then vanished into silence. The universe is full of mysteries, and that's exactly as it should be. Let those signals fade into the background of your awareness now, like distant music from a radio left on in another room. They're there, they'll always be there, but you don't need to solve them or understand them or even think about them anymore tonight. Just know that they exist, a gentle reminder that the cosmos is vast and strange and beautiful, and you're a small but real part of it, lying safely in your bed, breathing slowly, drifting peacefully towards sleep. Quantum entanglement, the universe's invisible threads. Now let's turn our attention to something smaller than galaxies and radio signals, something that exists at the tiniest scales imaginable, in the realm of atoms and subatomic particles, yet has implications that might extend across the entire universe. This is the phenomenon that Einstein famously called spooky action at a distance, a phrase that captures both the strangeness and the unsettling nature of what he was describing. We're talking about quantum entanglement, one of the most bizarre and well-verified predictions of quantum mechanics, and possibly one of the most profound clues we have about the fundamental nature of reality. Imagine two particles, perhaps two photons of light, that are created together in a particular way so that their properties become correlated. Let's say these particles have a property called spin, which you can think of as being like a tiny arrow that points either up or down. According to quantum mechanics, before we measure them, each particle exists in what's called a superposition, meaning it's both spin up and spin down simultaneously, like a coin that's spinning in the air and is neither heads nor tails until it lands. But here's where it gets interesting. If these two particles are entangled, then the moment you measure one particle and find that it's, say, spin up, the other particle instantly becomes spin down, no matter how far apart they are. They could be on opposite sides of a laboratory, on opposite sides of a planet, or on opposite sides of the universe, and this instantaneous correlation would still occur. The strange thing is that this doesn't seem like it should be possible. Einstein's theory of relativity tells us that nothing can travel faster than light, including information. If I measure one particle here on Earth and its entangled partner instantaneously knows what happened and adjusts accordingly, even though it's on Mars or in another galaxy, it seems like information has traveled faster than light. Einstein was deeply troubled by this, believing that quantum mechanics must be incomplete, that there must be hidden variables we're not aware of that predetermine what the measurement results will be, making the correlation only appear instantaneous when really both particles knew all along what they would do when measured. But experiments have proven Einstein wrong on this point. In the 1960s, physicist John Bell worked out a mathematical test that could distinguish between a universe where hidden variables exist and a universe where quantum entanglement is real. Experiments conducted over the following decades, using increasingly sophisticated techniques to close potential loopholes, have consistently confirmed that entanglement is real. The correlations between entangled particles are stronger than any hidden variable theory could explain. The universe really does contain these spooky connections that transcend space and time in ways that seem to violate our intuitions about how reality should work. Before you find this too unsettling, though, let's clarify something important. You cannot use entanglement to send information faster than light. Even though the particles are correlated, the measurement result you get on your end is always random. You might measure spin up or spin down, and you have no control over which result you'll get. Only when you compare your measurements with the measurements made on the other particle, after the fact, using normal slower-than-light communication, do you discover the correlation. So entanglement doesn't violate relativity's prohibition on faster-than-light communication. It's more subtle than that, more mysterious, as though the particles share something deeper than mere information, some underlying connection that exists outside of normal space and time. Physicists are still grappling with what entanglement really means and how it works. One interpretation, called the pilot wave theory or de Broglie theory, suggests that particles are guided by invisible fields that extend throughout space, and when particles become entangled, they're connected through these fields in ways we cannot directly observe. Another interpretation, the many worlds interpretation, proposes that every quantum measurement causes the universe to split into multiple branches, and the correlation we observe is because we're only seeing one branch while other branches contain the other possible outcomes. The standard Copenhagen interpretation simply says that quantum systems don't have definite properties until they're measured, and entangled systems must be treated as a single unified whole no matter how far apart their components are. Recent theoretical work suggests that entanglement might be even more fundamental than we thought. Some physicists are exploring the idea that space and time themselves might emerge from quantum entanglement, that the fabric of the universe is essentially woven from these connections between quantum particles. It's called the ER equals EPR conjecture, named after Einstein-Rosen bridges, wormholes, and the Einstein-Podolsky-Rosen thought experiment about entanglement. The idea is that when two particles are maximally entangled, they're connected by a microscopic wormhole, a tunnel through space-time that exists below the scales we can observe. As you add more and more entangled particles and more of these connections, the network of wormholes might build up to create the smooth fabric of space that we experience at larger scales. If this is true, if space itself is an emergent property of quantum entanglement, then the most fundamental level of reality isn't made of matter or energy or even space and time as we understand them. Instead, reality would be made of information, of correlations, of relationships between quantum systems. The universe would be, in a very real sense, made of connections rather than things, and the distances and separations we experience would be illusions arising from how these quantum connections are arranged. It's a dizzying thought, one that philosophers and physicists alike are still trying to fully comprehend, but it suggests that at the deepest level, everything truly is connected to everything else, not metaphorically but literally, through the invisible threads of quantum entanglement. Entanglement has practical applications too, though they're still mostly in the research stage. Quantum computers use entangled particles to perform certain types of calculations far faster than classical computers ever could. Quantum cryptography uses entanglement to create communication channels that are, in principle, perfectly secure because any attempt to eavesdrop would disturb the entangled particles and reveal the eavesdropper's presence. Scientists have even entangled particles across hundreds of kilometers using satellites, proving that these quantum connections can be maintained even when the particles are separated by the near vacuum of space. There's something deeply peaceful about entanglement, though, when you think about it in the right way. It tells us that separation is not absolute. Two things can be far apart in space and time yet remain profoundly connected, sharing a relationship that transcends distance. It's a scientific validation of an idea that appears in many philosophies and spiritual traditions, that at some level everything is interconnected, that the boundaries between things are less absolute than they appear, that what seems separate is actually part of a greater whole. Every particle in your body was once entangled with other particles, and some of those correlations might persist in subtle ways even now. The atoms that make up your cells were forged in the cores of ancient stars or in the violent explosions when those stars died, and during those processes, particles were entangled with each other in vast quantum networks. Those atoms were scattered into space, drifted through molecular clouds, eventually condensed into the solar nebula that formed the sun and planets, and billions of years later found their way into your body. All the while, quantum correlations were being created and destroyed, entanglements forming and breaking as particles interacted and separated, an invisible web of connection threading through everything that exists. In a very real sense, you are quantum mechanically connected to the rest of the universe in ways that we're only beginning to understand. Every breath you take, every photon of light that enters your eye, every atom in your body, they're all part of a vast network of quantum correlations that extends across space and time. You're not separate from the cosmos. You're woven into its very fabric through these invisible threads that Einstein found so spooky, these connections that transcend distance and causality and our everyday understanding of how things relate to each other. As you relax further into sleep, let that thought settle gently over you. The universe is not a collection of isolated objects but a unified whole, a single quantum state that includes everything from the smallest subatomic particle to the largest galaxy cluster. The boundaries between things, including the boundary between you and everything else, are conventional distinctions we make for practical purposes, but they're not fundamental. At the quantum level, the level that underlies all of reality, separation is an illusion, and connection is the deeper truth. Breathe slowly and feel yourself as part of this cosmic web of entanglement. You are connected to the earth beneath you through gravity and through the quantum correlations in every atom. The earth is connected to the sun through gravity and through the history of quantum interactions that occurred when the solar system formed. The sun is connected to the Milky Way, and the Milky Way to the local group of galaxies, and outward in a vast hierarchy of connection that ultimately encompasses everything that exists. You're not alone. You've never been alone. You're part of the universe's single, unified quantum state, entangled with everything, connected to it all in ways that transcend space and time. Let that thought be your lullaby tonight. The universe is holding you, has always held you, through invisible threads of quantum connection that can never be broken. You're safe within this cosmic web, a single point in an infinite network of entanglement, and you can rest now, peaceful and secure in your place within the whole. The great cosmic voids, oceans of nothing. While we've been talking about connections and hidden forces and mysterious signals, there's another aspect of the universe that deserves attention, perhaps especially when you're trying to fall asleep. We need to talk about emptiness, about the vast regions of space where almost nothing exists, stretches of darkness so immense that they make the distances between stars look like grains of sand separated by millimeters. These are the cosmic voids, and they occupy most of the universe's volume. If you could somehow zoom out and see the large-scale structure of the entire cosmos, what you'd observe would look remarkably like foam, like the bubbles in soap suds or the froth on top of a cappuccino. The galaxies aren't scattered randomly throughout space, but instead are arranged in filaments and sheets and clusters, forming a cosmic web that stretches across billions of light-years. And between these bright structures, occupying most of the volume, are the voids. Enormous, nearly empty regions where galaxies are rare and matter is sparse. Bubbles in the cosmic foam that can span hundreds of millions of light-years from one side to the other. The Boötes void, sometimes called the Great Nothing, is one of the most famous examples. Discovered in 1981 by astronomer Robert Kirshner and his team, this nearly spherical region is about 330 million light-years across. When astronomers first mapped it, they were stunned by how empty it was. A typical region of space that size should contain about 2,000 galaxies, but the Boötes void contains only 60. It's as though someone scooped out a portion of the universe and left only the faintest traces behind. Why do these voids exist? The answer lies in how the universe evolved from its earliest moments. Shortly after the Big Bang, matter and energy were distributed almost uniformly throughout space, but not quite uniformly. There were tiny fluctuations in density, quantum ripples from the inflationary period that had been stretched to cosmic scales. In regions where matter was slightly denser than average, gravity began pulling more matter in, causing those regions to become denser still. In regions where matter was slightly less dense, gravity pulled matter away toward the denser regions, causing those areas to become emptier over time. This process is called gravitational instability, and it's driven by a positive feedback loop. Dense regions get denser while empty regions get emptier. Over hundreds of millions and billions of years, this process sculpted the universe into the cosmic web we see today. Matter flowed along the paths of least resistance, forming filaments that connect dense nodes where galaxy clusters formed. The regions between the filaments, the cosmic voids, were gradually evacuated as their matter drifted away toward the denser structures. It's like watching water drain from a bathtub, collecting in certain areas while leaving others dry, except instead of water it's galaxies, and instead of a bathtub it's the entire observable universe, and instead of minutes it took billions of years. But the voids aren't completely empty. Sophisticated observations can detect faint dwarf galaxies scattered through them, and computer simulations reveal that dark matter still permeates the voids in tenuous filaments and strands, invisible echoes of the grand cosmic web repeating at smaller scales. If you could somehow venture into the deepest part of a cosmic void, far from any galaxy, you'd find that space still has matter in it, just very sparsely distributed. The average density might be as low as 1 hydrogen atom per cubic meter, compared to the overall cosmic average of about 1 atom per cubic meter and the much higher densities found in galaxies and galaxy clusters. You could swim through the deepest voids and encounter a single atom in an entire football field's worth of space. What would it be like to float in such emptiness? The darkness would be profound, broken only by the faintest light from distant galaxies billions of light-years away around the void's periphery. There would be no nearby stars, no galaxies anywhere near you, just vast, uninterrupted darkness in every direction. The temperature would be close to absolute zero, with almost no radiation to warm you. Time would seem to stand still because there would be so few events occurring, so little change, just the slow, patient expansion of space itself stretching the void larger with each passing moment. And yet, even in this emptiness, dark energy would be at work. In fact, voids are the places where dark energy shows itself most clearly. Within galaxies and galaxy clusters, gravity is strong enough to overcome dark energy's repulsive effect, holding matter together against the expansion of space. But in the voids, there's so little matter and therefore so little gravitational attraction that dark energy dominates completely. The voids are expanding faster than the universe as a whole, growing emptier as the dark energy woven into the fabric of space pushes them outward, accelerating their expansion, creating more space between the already sparse matter they contain. Scientists study voids because they're like natural laboratories for understanding cosmology. The simplicity of voids, their lack of complicated structures like galaxies and stars, makes them ideal for testing theories about how the universe works on the largest scales. By measuring how voids have evolved over cosmic time, how they're distributed in space, how matter moves around them, astronomers can test predictions from general relativity and compare different models of dark energy and dark matter. It's like studying a still pond to understand the properties of water, whereas studying galaxies is like trying to understand water by observing a waterfall or a storm at sea. There's a strange beauty to voids when you contemplate them. They're the ultimate minimalist art, vast canvases with almost nothing painted on them, allowing the subtle properties of space itself to become visible. In our everyday lives, we're surrounded by complexity. Objects, people, information, stimulation coming at us constantly from all directions. But the voids remind us that most of the universe is emptiness, quiet and dark and simple. They're nature's meditation on the theme of nothingness, proof that you don't need to fill every space, that emptiness has its own value and meaning. The KBC void, named after astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, is special because we might be living in it. Some evidence suggests that the Milky Way galaxy and our local group of galaxies are located near the edge of a void about 2 billion light-years across, with a density about 20% lower than the cosmic average. If this is true, it could help explain some puzzling measurements astronomers have been making about the expansion rate of the universe. The Hubble tension, as it's called, refers to the fact that measurements of how fast the universe is expanding give different answers depending on whether you measure nearby or distant parts of the cosmos. If we're in a void, the local expansion rate would appear faster than the true cosmic average, potentially explaining at least part of this discrepancy. Think about that as you lie in your bed, a tiny speck on a planet orbiting a star in a galaxy that might itself be floating through a vast region of relative emptiness. You're surrounded by void, cosmically speaking, living in one of the bubbles in the cosmic foam. And yet this bubble is all you'll ever know or experience. The void is so vast that even if we could travel at the speed of light, it would take hundreds of millions or billions of years to cross it to reach the filaments and clusters beyond. For all practical purposes, our cosmic neighborhood, this section of the universe we can observe and interact with, is all there is. There's something reassuring about voids as you're drifting towards sleep. They teach us that emptiness is not absence but presence, that nothing is still something. The voids are full of dark energy, full of the quantum vacuum with its fields and virtual particles, full of the curvature of space-time itself. They're spaces where the universe has room to breathe, to expand, to exist without the compression and complexity of galaxies and stars. Their cosmic restfulness made physical, vast, quiet regions where almost nothing happens, and that's perfectly fine. Let the idea of voids wash over you now. Imagine yourself floating in that profound darkness, surrounded by nothing in particular, with no urgency and no demands. There's peace in emptiness when you stop fearing it and start accepting it. The voids have existed for billions of years, will exist for billions more, patient and serene, doing nothing but occupying space and slowly expanding. They make no sound, emit almost no light, exert almost no influence, and yet they're essential to the universe's structure, the quiet between the notes that makes the melody meaningful. Breathe into that emptiness. Let your mind become like a void, dark and quiet and spacious, with thoughts drifting through occasionally like rare faint galaxies, but mostly just existing in peaceful stillness. There's nothing you need to do, nowhere you need to be, nothing to figure out or solve. Just rest in the emptiness the way the voids rest in the cosmos, content to simply be. Black holes where physics breaks down. In the centers of most large galaxies, including our own Milky Way, there lurks something that challenges our understanding of reality itself. These are the supermassive black holes, objects containing millions or billions of times the mass of the Sun compressed into a region smaller than our solar system, and they represent perhaps the most extreme environments in the universe, places where the normal rules of physics reach their breaking point and possibly shatter entirely. A black hole is what remains when a massive star exhausts its nuclear fuel and collapses under its own gravity, or when enormous amounts of matter accumulate in one place and collapse together. The collapse continues until all that mass is compressed into an infinitesimally small point called a singularity, a location where density becomes infinite and the equations of general relativity break down. Around this singularity is a boundary called the event horizon, a point of no return beyond which nothing, not even light, can escape the black hole's gravitational pull. The name event horizon is wonderfully evocative. It's a horizon in the truest sense. Beyond it, you cannot see what's happening, just as you cannot see beyond Earth's horizon when standing on the ground. But unlike Earth's horizon, which you can cross by walking or flying, a black hole's event horizon is absolute. Once you cross it, there's no coming back, no way to send information or light or anything else back across to the outside universe. You've passed into a region of space-time that is, in a very real sense, disconnected from the rest of existence. What happens if you fall into a black hole? The answer depends on your perspective. If you're falling in, you'd notice something very strange happening. As you approach the event horizon, time would seem to pass normally for you. You might not even notice the exact moment when you cross the boundary. But if you looked back at the universe you were leaving behind, you'd see something remarkable. Events would appear to speed up dramatically. Stars would rush through their life cycles, galaxies would evolve and fast forward. And if you could somehow survive long enough, you might watch the entire future of the universe unfold in moments before you. Meanwhile, to an outside observer watching you fall, something completely different would appear to happen. As you approach the event horizon, you'd seem to slow down, moving more and more sluggishly as gravitational time dilation becomes extreme. You'd appear to freeze, asymptotically approaching the event horizon but never quite reaching it. your image becoming redder and dimmer as light from your body becomes increasingly redshifted and stretched out. From the outside universe's perspective, you'd never cross the event horizon at all. You'd just fade away, becoming dimmer and dimmer, approaching but never arriving, frozen at that boundary between inside and outside forever. Both perspectives are equally valid. This is one of the strange consequences of relativity. What seems like a straightforward question, what happens when you fall into a black hole, has fundamentally different answers depending on who's asking. Time and space become so warped near a black hole that simultaneity breaks down entirely. The moment when you cross the event horizon in your reference frame simply doesn't exist in the reference frame of someone watching from far away. Once past the event horizon, things become even stranger. Space and time exchange roles in a certain sense. In ordinary space-time, you can choose where to go in space, but you're forced to move forward in time. You can turn around and walk back to where you came from, but you can't travel backward in time to yesterday. Inside the event horizon, the singularity lies in your future in the same way that tomorrow lies in your future outside. You can no more avoid falling into the singularity than you can avoid experiencing tomorrow. It's inevitable not because any force is pulling you toward it, but because that's the way time flows in that region of space-time. At the singularity itself, all our physical theories fail. General relativity predicts that density becomes infinite, curvature becomes infinite, and the very fabric of space-time tears itself apart. Quantum mechanics adds additional complications. At the incredibly small scales of a singularity, quantum effects should become important, but we don't have a working theory of quantum gravity to tell us what actually happens. The singularity is a place where our knowledge ends, where the equations produce infinities and nonsense, telling us that we're asking questions we don't yet know how to formulate properly. This is the black hole information paradox, one of the deepest mysteries in theoretical physics. When matter falls into a black hole, it seems like the information about that matter is destroyed. A book, a computer, a human being, all the complexity and information they contain appears to be erased at the singularity, leaving behind only the black hole's mass, charge, and rotation. But quantum mechanics says that information cannot be destroyed, that it must be preserved in some form even if it becomes scrambled beyond recognition. So what happens to information that falls into a black hole? Does it really vanish, violating quantum mechanics? Or is it somehow encoded on the event horizon, or released in the subtle radiation that Stephen Hawking predicted black holes would emit? Hawking radiation is itself a fascinating phenomenon arising from the quantum properties of empty space near the event horizon. Due to quantum fluctuations, pairs of particles and antiparticles constantly pop into existence throughout space, normally annihilating each other almost immediately. But near a black hole's event horizon, it's possible for one particle to fall into the black hole while its partner escapes. To an outside observer, it appears that the black hole is emitting radiation, very slowly leaking away its mass as these quantum effects siphon energy from it. For a stellar mass black hole, this radiation is incredibly faint, far colder than the cosmic microwave background. But for tiny microscopic black holes, if they exist, the radiation could be intense enough to cause them to explode. If Hawking radiation is real, and most physicists believe it is, then black holes will eventually evaporate. Given enough time, trillions upon trillions of years, even supermassive black holes will radiate away all their mass and disappear, leaving nothing behind. But this raises the information paradox again. If the black hole evaporates completely, what happened to all the information about everything that fell in? Is it somehow encoded in the Hawking radiation in a way so subtle we don't understand it yet? Or does the black hole leave behind a remnant, a tiny but stable object that somehow contains all that information compressed into it? Or is our understanding of quantum mechanics or general relativity or both fundamentally flawed? Recent theoretical work suggests a possible resolution through the holographic principle, the idea that information about a volume of space can be encoded on its boundary surface, like a hologram that contains three-dimensional information on a two-dimensional surface. Perhaps information that falls into a black hole is actually stored on the event horizon in an incredibly scrambled form, and as the black hole radiates via Hawking radiation, that information is slowly released back into the universe, though in such a jumbled state that it would be nearly impossible to reconstruct what fell in. This would preserve the quantum mechanical principle that information is never destroyed while still accounting for the apparent loss of information when things fall past the event horizon. Black holes are the universe's way of showing us the limits of our current understanding. They're extreme physics laboratories that we cannot visit or directly experiment with, but that nature has provided for us to study from a distance. The mere existence of black holes tells us that our theories of gravity and quantum mechanics, successful as they are within their domains, cannot both be correct in their current form. Somewhere in the heart of a black hole, those theories must give way to something deeper, some theory of quantum gravity that unifies the very large and the very small, that explains what happens when extreme mass and energy are compressed into incomprehensibly small spaces. For our purposes tonight, though, black holes serve as a reminder that there are boundaries to knowledge, places where our maps run out and we must admit ignorance. At the event horizon, causality as we understand it reaches a limit. Beyond it lies a region we can never observe, never study directly, never retrieve information from. It's a cosmic censorship of sorts, a built-in feature of the universe that prevents us from witnessing the breakdown of physical law at the singularity. We can theorize about it, we can calculate, we can simulate, but we cannot know for certain what happens in those deepest regions where reality itself might be fundamentally different from everything we've experienced. And yet black holes are real. There's one at the center of our galaxy, 4,000,000 times the mass of the Sun, around which hundreds of billions of stars orbit like moths around a flame. We've photographed the event horizons of supermassive black holes in other galaxies, seeing the characteristic shadow surrounded by a ring of light from matter spiraling in. We've detected gravitational waves from black holes colliding and merging, sending ripples through space-time that propagate across billions of light-years to shake our detectors by distances smaller than an atomic nucleus. Black holes are not speculation or fantasy. They're as real as anything in the universe, and they're telling us something profound about reality's structure, if only we could fully understand the message. Let yourself sink into the mystery of black holes as you sink into sleep. There's something oddly comforting about knowing that not everything can be understood, that the universe contains genuine mysteries that might never be completely solved. Our ignorance is not a failure but a feature, a sign that reality is richer and stranger than any theory we've yet devised. The singularity at a black hole center is a question mark written into the fabric of space-time, a place where the universe shrugs and says, "I don't know," to all our inquiries. And that's perfectly fine. We don't need to understand everything. We don't need to solve every mystery or see past every horizon. We can rest in the knowledge that there are still frontiers, still unknowns, still places where wonder lives. Close your eyes and imagine an event horizon, that perfect sphere in space where light itself is trapped, where time slows to a stop from an outside perspective, where the rules change and the familiar becomes strange. You're safely outside it, far from any real black hole, lying in your comfortable bed on a stable planet orbiting a normal star. But in your imagination, you can contemplate that boundary between the known and the unknown, that place where physics admits its limits and mystery takes over. Let that boundary be a metaphor for the edge of consciousness as you drift towards sleep, crossing from the waking world into dreams, from thought into thoughtlessness, from awareness into rest. Time's mystery, the beginning and the end. Of all the things we take for granted in our daily lives, time might be the most mysterious when you examine it closely. We experience time as flowing from past through present into future, an irreversible stream that carries us forward whether we want to go or not. Yet the fundamental laws of physics, particularly at the quantum level, don't distinguish between past and future. The equations work equally well whether time is running forward or backward. So where does this arrow of time come from? This sense that the past is fixed and the future is open, that eggs can break but never spontaneously reassemble, that we remember yesterday but not tomorrow. The answer seems to involve entropy, a measure of disorder or randomness in a system. The second law of thermodynamics states that entropy in a closed system always increases over time. This gives us an arrow of time. Entropy was lower in the past and will be higher in the future. An intact egg has lower entropy than a scrambled egg, so eggs break and become scrambled but never the reverse. Heat flows from hot to cold, not cold to hot. Gases mix together but never spontaneously separate. Everything tends toward disorder, and that tendency gives time its direction. But this just pushes the mystery back a step. Why was entropy so low in the early universe? When we look at the cosmic microwave background radiation, the afterglow of the Big Bang, we see that the universe 13 billion years ago was remarkably uniform and smooth. That smoothness represents very low entropy. It's as though the universe began in an incredibly ordered state, and all the complexity and structure we see today, all the galaxies and stars and planets and life, represents entropy increasing as the universe evolves. Where did that initial low entropy state come from? This is one of the deepest questions in cosmology. The standard Big Bang theory describes how the universe evolved from a hot, dense state, but it doesn't really explain why the universe began in that particular low-entropy configuration. The theory of cosmic inflation attempts to address this by proposing that before the hot Big Bang, there was a period when a quantum field drove a period of exponential expansion, stretching a tiny region of space to enormous size and setting up the conditions for the Big Bang proper. But inflation itself needs to be explained. What caused inflation? What existed before inflation? Why did the inflationary field exist in the first place? Some physicists suggest that asking what came before the Big Bang might be like asking what's north of the North Pole. If time itself began with the Big Bang, if the concept of before only makes sense within the universe, then there might not be a meaningful answer to the question of what preceded it. Others propose that the Big Bang was not the beginning but rather a transition from a previous state, perhaps the collapse of a previous universe or a quantum fluctuation in some eternally existing multiverse. The honest answer is that we don't know, and we may never know, because the earliest moments of the universe might be forever beyond the reach of observation and experiment. Then there's the question of how the universe will end. The answer depends largely on dark energy. If dark energy remains constant, the universe will continue expanding forever at an accelerating rate. Eventually, in the incredibly distant future, galaxies will recede beyond each other's cosmic horizons. The stars will exhaust their fuel and go dark. Black holes will evaporate via Hawking radiation. After an unimaginably long time, perhaps 10 to the power of 100 years, the universe will be a cold, dark, expanding void containing nothing but a thin soup of elementary particles at a temperature infinitesimally above absolute zero. This is sometimes called heat death, though it's really more like cold death, the universe achieving maximum entropy, a state where nothing interesting can ever happen again because there are no energy gradients left to power any processes. If dark energy grows stronger over time, the fate could be even more dramatic. In a scenario called the Big Rip, the accelerating expansion eventually becomes so powerful that it tears apart galaxies, then stars, then planets, then molecules, then atoms, and finally even atomic nuclei and subatomic particles, reducing everything to a sea of disconnected elementary particles or energy. The universe would end not in a whimper of heat death, but in a violent crescendo of expansion that rips apart the very fabric of matter itself. Alternatively, if dark energy could somehow reverse or decay away, gravity might eventually win, causing the expansion to slow, stop, and reverse. The universe would begin contracting, galaxies would start moving toward each other rather than away, and eventually everything would collapse back into a hot, dense state in a big crunch, possibly followed by a big bounce into a new cycle of expansion. In this cyclic model, which has ancient roots in various philosophies and religions, the universe might be eternal, oscillating through infinite cycles of expansion and contraction, big bangs and big crunches repeating forever. But all of these endings are so far in the future that contemplating them has no practical relevance. The sun will die in about 5 billion years, long before any cosmic ending matters. The Earth will be consumed when the sun expands into a red giant. Any descendants of humanity, if there are any, will have long since spread to other stars or evolved beyond recognition. The ending of the universe is someone else's problem, a problem for beings and civilizations that don't yet exist and might never exist, in a future so distant that the word future seems inadequate. Time is also mysterious in more immediate ways. Einstein showed that time is relative, that it flows at different rates depending on how fast you're moving and how strong the gravitational field is around you. Satellites in orbit experience time slightly faster than people on Earth's surface, about 38 microseconds per day faster, because they're higher up in Earth's gravitational well. This effect has to be corrected for in GPS systems, or the positioning calculations would drift by miles over the course of a day. Near a black hole's event horizon, time dilation becomes extreme. What seems like an hour to you might be years or centuries to someone far away from the black hole. Some physicists have proposed that time might not be fundamental at all. In certain approaches to quantum gravity, time emerges from more basic, timeless principles in a similar way that temperature emerges from the motion of molecules. At the most fundamental level, reality might be timeless, and the flow of time we experience might be an illusion or approximation that only makes sense for complex systems like ourselves. This is speculative but fascinating. The idea that past, present, and future might all exist simultaneously in some deeper sense, and our experience of moving through time is like reading a book page by page, creating the illusion that the pages ahead don't exist yet when really the entire book exists as a complete entity. For tonight, though, the practical mystery of time is simpler. The mystery of how consciousness transitions between waking and sleeping, how hours can pass in what feels like moments, how the structured time of daily life gives way to the timeless drift of sleep and dreams. When you're awake, you're embedded in time, aware of it passing, planning for the future, remembering the past. When you're asleep, especially in deep dreamless sleep, time becomes irrelevant. Hours pass, but you don't experience their passing. It's as close as you can come while alive to existing outside of time. Let yourself approach that timeless state now. Stop planning, stop remembering, stop being aware of the clock or the passage of minutes. Let time become meaningless. You're floating in a place where there is no before and no after, no yesterday and no tomorrow, only this eternal present moment that stretches and expands until it contains everything. The universe began 13 billion years ago and might end in trillions of years, but that's the universe's concern, not yours. Right now, for you, time can stop or slow or disappear entirely as you sink into sleep. The great physicist John Wheeler once said that time is what prevents everything from happening at once. As you drift toward sleep, you're moving toward a state where that prevention lifts, where the boundaries between moments blur and dissolve, where past and future collapse into an eternal now. The universe has existed for billions of years and will exist for billions more, but this moment, this peaceful transition toward sleep, this is the only moment that exists for you, and it's perfect exactly as it is. Breathe slowly and let time become elastic, stretching and thinning until it's as transparent and insubstantial as a soap bubble. You don't need to worry about tomorrow, you don't need to think about yesterday, you don't need to keep track of now. Just rest in timelessness, in the eternal present that has no past or future, no beginning or end, no forward or backward, just existing beyond time, beyond change, beyond thought, in perfect, peaceful stillness. The question of existence. Where is everyone? As we near the end of our journey through cosmic mysteries, we come to perhaps the most profound question of all, one that touches on our place in the universe and what it means to be alive and aware in this vast cosmos. This is the Fermi paradox, named after physicist Enrico Fermi, who supposedly asked during a casual conversation, "Where is everybody?" He was referring to extraterrestrial civilizations, and his question highlighted a troubling contradiction. The universe is incomprehensibly large, containing hundreds of billions of galaxies, each with hundreds of billions of stars, many of those stars with planets, some fraction of which must be capable of supporting life. Even if the chances of life arising on any given planet are vanishingly small, the sheer number of planets should make it almost certain that life has arisen countless times throughout the universe. And if life has arisen many times, then at least some of it should have evolved intelligence, and at least some intelligent civilizations should have developed technology, and at least some technological civilizations should have started expanding beyond their home worlds, colonizing their solar systems and eventually their regions of the galaxy. Given that the universe is billions of years old, there's been plenty of time for such expansion. Where are they? Why don't we see evidence of alien civilizations everywhere we look? Various solutions to the paradox have been proposed. ranging from the optimistic to the sobering to the outright disturbing. Perhaps we're alone, the first and only intelligent civilization in our galaxy or even in the observable universe. This seems unlikely given the vastness of space and the number of opportunities for life, but it's possible. Perhaps life is common but intelligence is rare, or technological civilization is a brief phase that most species pass through quickly before destroying themselves or evolving into something we wouldn't recognize. Perhaps civilizations do arise and spread, but they're so far away that we simply haven't encountered them yet, and we won't for millions or billions of years. Perhaps intelligent life is common but tends to stay hidden, either deliberately avoiding contact with other civilizations or existing in forms we can't detect. Maybe they've transcended physical form, uploading themselves into computers or virtual realities, or evolving into beings of pure energy or information. Maybe they're all around us, but we can't perceive them because they exist in different dimensions or their technology is so advanced it appears to us as natural phenomena. The zoo hypothesis suggests they know about us but are deliberately not interfering, observing us the way we might observe animals in a nature preserve, letting us develop on our own without contaminating us with their presence. Or perhaps the great filter exists, some barrier that prevents most civilizations from advancing past a certain point. The filter could be in our past. Maybe it's incredibly difficult for life to originate from non-living chemistry, or incredibly difficult for complex multicellular life to evolve from simple cells, or incredibly difficult for intelligence to emerge. If the filter is behind us, then we're extraordinarily lucky to have made it this far, but our future is potentially bright. But if the filter is ahead of us, if there's some disaster or limitation that virtually all civilizations encounter once they reach our level of development, then our future is bleak, and the silence we observe in the cosmos is a warning of what awaits us. The most unsettling possibility is that civilizations are common but short-lived, typically destroying themselves through nuclear war, environmental collapse, artificial intelligence gone wrong, nanotechnology run amok, or some other catastrophe that we haven't even thought of yet. If this is true, then the universe might be full of ruins and graveyards, dead worlds where civilizations briefly flourished and then disappeared, leaving behind nothing but silence and perhaps a few technological artifacts that decay slowly in the cold of space. The great silence we observe might be not because civilizations are rare, but because they're fragile, burning bright for a few centuries or millennia before extinguishing themselves. But let's consider a more peaceful interpretation, one appropriate for falling asleep. Perhaps the reason we haven't encountered alien civilizations is simply that space is vast and travel between stars is difficult. Even traveling at a significant fraction of the speed of light, it would take decades or centuries to reach even the nearest stars, and there are hundreds of billions of stars in our galaxy alone. Even if civilizations do spread outward from their home worlds, that expansion might be slow, taking millions of years to colonize even a small region of a galaxy. And if civilizations arise at random times and places, the chances that two civilizations would overlap in space and time in a way that allows them to meet might be vanishingly small. Furthermore, perhaps advanced civilizations simply have no interest in expansion or contact. Once a civilization develops certain technologies, perhaps they find it more interesting to explore inner space rather than outer space, to develop sophisticated virtual realities, or to modify their own consciousness rather than to build starships and colonies. Perhaps they retreat inward, creating ever more complex and beautiful worlds of thought and experience within their own minds or computers, finding the entire universe and all of existence contained in the space of consciousness itself. There's something both lonely and comforting about our cosmic isolation. Lonely because it might mean we're truly alone, or at least alone enough that we'll never meet our cosmic neighbors, that the human experience is unique and unshared. But comforting too because it means that this planet, this solar system, this corner of the galaxy is ours to steward and care for, that the responsibility and the opportunity lie with us and no one else. We're not someone else's problem to solve or someone else's experiment to run. We're simply here, existing in this particular time and place, part of the universe becoming aware of itself, matter organized in such a way that it can wonder about its origins and contemplate its fate. Every time you look up at the night sky, you're looking at questions without answers. Those stars, those points of light scattered across the darkness, some of them certainly have planets, and some of those planets might harbor life, and some of that life might be intelligent, might be looking back at our sun and wondering the same questions. Are we alone? Will we ever meet? What does it mean to exist in a universe so large that even at the speed of light, signals would take millions or billions of years to travel from one civilization to another? But maybe those questions don't need answers. Maybe it's enough to exist, to be conscious and aware, to experience the universe from this particular vantage point. You are the universe looking at itself, a small part of the cosmos that has become complex enough to wonder about the whole. Your existence is improbable, precious, temporary. You're made of atoms forged in stars, arranged through evolution into a pattern capable of thought and feeling and wonder. Right now, lying in your bed, you're participating in one of the universe's most remarkable achievements. Self-awareness, consciousness, the emergence of something that can know and question and marvel at the cosmic story of which it's a part. The silence of the cosmos, if it is silence, is not empty but full. It's full of possibilities, of potential, of mysteries waiting to be discovered. Whether we're alone or surrounded by neighbors we haven't met yet, whether the universe is teeming with life or we're a unique accident, the important thing is that you're here now, experiencing this moment, part of the grand cosmic unfolding that's been happening for billions of years and will continue for billions more. Let that thought settle over you like a warm blanket. You are, therefore you matter. Your existence is significant not because you have some grand cosmic purpose or destiny, but simply because you exist, because you're here, because you're part of this, whatever this is. The universe might be silent, space might be empty, we might be alone, but that doesn't diminish the value or the beauty or the wonder of existence itself. It just means that existence is rarer and more precious than we might have hoped, that consciousness is a gift we shouldn't take for granted. Close your eyes now and feel yourself as a citizen of the cosmos, a child of the stars, a temporary pattern of matter and energy that has emerged from the universe and will one day return to it, but for now, for this brief span of time, exists and experiences and knows. There might be others like you out there somewhere in the vastness, or there might not be. But either way, you are here, you are real, you are part of the mystery and the beauty and the incomprehensible wonder of it all. The piece of mystery. And so we've traveled together through some of the deepest mysteries the universe has to offer. We've contemplated dark matter, invisible yet essential, holding galaxies together with its hidden gravitational grip. We've explored dark energy, that mysterious force accelerating the universe's expansion, pushing everything apart with patient inevitability. We've listened to strange signals from space, fast radio bursts and long-period transients, and that tantalizing wow. signal that appeared once and never again. We've marveled at quantum entanglement, those invisible threads connecting particles across space and time in ways that defy our everyday intuitions about how reality works. We've floated through cosmic voids, those vast empty regions that occupy most of the universe's volume, teaching us that nothingness has its own presence and meaning. We've approached the event horizons of black holes, those boundaries beyond which our physics breaks down and mystery takes over completely. We've contemplated time itself, its arrow, its beginning, its eventual end, and its mysterious relationship to consciousness. And we've pondered the great silence, the question of whether we're alone in the cosmos or simply haven't yet met our neighbors. Through all of this, a common theme has emerged. The universe is far stranger and more wonderful than our everyday experience suggests, and most of it remains deeply mysterious despite all our scientific advances. We live in a reality where most of what exists is invisible to us, where the laws of physics allow for phenomena that seem impossible, where the very fabric of space and time is woven from principles we're only beginning to understand, where consciousness has emerged from unconscious matter in ways we cannot explain, where the question of whether we're alone remains unanswered despite all our searching. But rather than finding this troubling, you can let it be a source of comfort and wonder. The universe doesn't need to be completely understood to be appreciated. Mystery isn't a problem to be solved, but a permanent feature of existence. A reminder that there will always be frontiers, always unknowns, always places where our maps end and we must admit the limits of our knowledge. And that's beautiful. That's perfect. That's exactly as it should be. As you lie there now, feeling yourself sinking deeper into sleep with each breath, let all these mysteries exist together in your mind like stars in a constellation. They're connected not by understanding but by wonder, by the shared recognition that reality is richer and deeper than any explanation we've devised. Dark matter and dark energy, quantum entanglement and cosmic voids, black holes and the arrow of time, the beginning and the end, the silence of space and the question of our place within it, all of these are threads in a single cosmic story that's still being written. You don't need to solve these mysteries or understand them completely. You don't need to have answers to the questions they raise. It's enough to know that they exist, to have spent this time contemplating them, to have let your mind expand to encompass these vast cosmic wonders. In doing so, you've placed yourself in the proper context. You're small but not insignificant, temporary but real, part of something so much larger than yourself that it's almost incomprehensible. Before you drift off completely, take a moment to appreciate the miracle of this moment. You're lying safely in your bed, protected from the vacuum of space by an atmosphere that happens to be exactly right for your survival, warmed by a star that happens to be the right type and the right distance to make life possible, anchored to a planet by gravity that happens to be strong enough to hold you but not so strong as to crush you, surrounded by darkness but not the absolute darkness of cosmic voids, experiencing time but not yet worried about its ending, alone perhaps in this room, but part of the vast cosmic web of existence that connects everything to everything else through the invisible threads of physics and chemistry and quantum mechanics. Everything is as it should be. The mysteries remain unsolved. The universe continues its expansion. Dark energy pulls space apart while gravity tries to hold it together. Quantum particles remain entangled across impossible distances. Voids stay empty. Black holes guard their secrets. Time flows forward, and somewhere out in that vast cosmos, There might be someone else lying in bed contemplating these same mysteries, or there might not be. And either way, it's fine. It's all fine. Everything is unfolding exactly as it must. Your breathing has slowed now, becoming deeper and more regular. Your body has relaxed completely, releasing the tension of the day, letting go of concerns and worries and plans. Your mind is quiet, no longer grasping at thoughts but simply existing in peaceful awareness, like a cosmic void that contains almost nothing and yet is full of potential, full of the quantum vacuum, full of space itself. You're drifting now, floating in darkness that's comfortable and safe, suspended between waking and sleeping, between thought and non-thought, between existence and whatever lies beyond. If you've enjoyed this journey through the cosmos and these contemplations of mystery, I hope you'll consider liking this video and subscribing to Deep Science Sleep for more explorations like this one. We'll continue to investigate the wonders and mysteries of science in ways that help you relax, find perspective, and drift peacefully into sleep. The universe has infinite stories to tell, countless phenomena to explore, and we're just getting started on this journey of discovery and wonder. But for now, let it all fade away. The mysteries will still be there tomorrow. The universe will continue its patient unfolding, and you've done everything you needed to do tonight simply by listening, by contemplating, by allowing yourself this time to rest and wonder. The dark matter surrounds you. The dark energy expands around you. Quantum entanglement connects you to everything that exists. The cosmic voids stretch endlessly in all directions. Black holes guard their secrets in the hearts of galaxies. Time carries you forward into dreams, and whether we're alone or surrounded by cosmic neighbors, you are here, you are real, you are enough. Sleep now, rest in mystery. Let the universe continue its grand story while you drift into dreams, peaceful and safe, surrounded by wonders you don't need to understand, held by forces you don't need to comprehend, part of something vast and beautiful and strange and perfect exactly as it is. Good night, and thank you for journeying through these cosmic mysteries with me. May your sleep be deep, your dreams be peaceful, and your rest be complete. The universe watches over you, patient and eternal, and everything is exactly as it should be.